Hello, and a big welcome back to all my subscribers. And if you're not a subscriber, why not? Today I'm going to continue with the RISC-V processors, and today we're going to look at the registers and the stack. Just an overview of the RISC-V registers. So RISC-V is an open standard instruction set, and it's based on the reduced instruction set computing principles. And one of its core features is the utilization of a set of registers which are small but fast storage locations which are located directly inside of the CPU. So these registers play a critical role in the execution of programs because they store data that is immediately needed for operations, including arithmetic, logical operations, memory addressing for accessing data, and control execution for the flow of execution. So now the RISC-V has 32 general purpose registers, and each of these registers are the 32-bit wide from a 32-bit system, but they're 64 bits wide on a RV64i variant. So these registers are named from X0 to X31. And register 0 is hardwired to be 0, meaning it always contains the value 0 and it cannot be overwritten or changed. And the other registers, X1 to X31, are used for various purposes, including holding temporary data, function arguments, functional return values, etc. Now, besides the general purpose registers, RISC-V has several special registers that serve specific functions within the architecture. The two most notable of these are the program counter, or PC. The program counter is a special register that holds the memory address of the next instruction to be executed. It's automatically updated after each instruction, and it pointing to the subsequent instruction in the sequence. And the PC ensures that the subsequent execution of the code, although you can modify the PC with jump and branch instructions, that alter the flow of the execution. And the next important one is the stack pointer. Stack pointer is traditionally held in register X2 in RISC-V, and it points to the top of the current stack of memory. Now, the stack is a crucial data structure used for managing function calls, including passing arguments, handling return addresses, and local variables. The stack pointer is automatically adjusted when data is pushed onto or popped off the stack. And we're going to look at that more closely today. Now, RISC-V adopts a set of conventions regarding how registers are used, and it's aimed at improving the efficiency of function calls and the predictability of behavior. Now, these conventions are part of the application of binary interface that defines how software interfaces are going to happen. And the key register conventions are shown here. So X0 always holds the value of 0. X1 is RA, which is return addresses. X2 is the stack pointer. X3 is the global pointer, which points to the middle of the allocated global data. X4 is a thread pointer used for thread local storage. Now, X5 through X7 is aliased as T0, T2, and these are temporary registers used to hold intermediate values. X8 is the frame pointer, and it's used to hold the base of the current stack frame. Now, X9 or S1 is saved register 1, and this is for holding values that can be preserved across function calls. Because if you remember before, I have said that if you don't put it in the right register, it'll get clobbered after a function call, and all of the data will be lost. So you should hold them in an S register, and hence these aliases and naming conventions. Now, A0 and A1, function arguments and return values. The first two arguments to functions and their return values. X12 through 17, aliased as A2 through A7. Again, these are function arguments for passing additional arguments. X18 through 27 are S2 through S11. So these are saved registers, and they hold values that can be preserved across function calls. And then we have X28 through 31 is T3 through T6. So these are more temporary registers used for storing various storage principles. So understanding and adhering to these register conventions is crucial when you're beginning assembly language program, because it ensures compatibility with existing code, it facilitates interoperability between different pieces of software, and it helps to maintain a clear structure within your programs. And as you grow more accustomed to programming with RISC-V, these conventions will become second nature. You rarely ever use the X names. You generally would use the aliases almost always. And they just become second nature, and it'll help you a lot when you're developing programs in assembly. Now, in computer architecture, data is most often discussed in terms of its size or the amount of memory it occupies. So the basic unit of data is a bit, which can either be a 0 or a 1. And from bits, larger units are constructed, notably bytes, words, double words, and so on. Now, these terms help to understand how the data is organized, stored, and manipulated by computer systems. This is much more important in assembly language than other higher-level languages. Now, a byte is traditionally the basic unit of data and consists of 8 bits. So a byte can represent 256 different values, or 2 to the 8th. And it ranges from 0 to 255 in a decimal notation. It's standard chunk of memory used to represent a character in many schemes like ASCII. A word is the size of the word is very architectural dependent, and it usually aligns with the native size of the registers in the CPU. So a word can be 16 bits or 2 bytes on some older processors, 32 bits or 4 bytes in most modern 32-bit architectures, or 64 bits or 8 bytes is a word on a 64-bit architecture. Now, in a 32-bit architecture, that 8 bytes would traditionally be called a double word. Now, the term word signifies a standard unit of data, and the word is the amount of data that can be processed by the CPU in one operation. Now, a double word is twice the size of a word. So 32 bits or 4 bytes on a system where a word is 16 bits, 64 or 8 bytes in a system where it's 32 bit word size. But it's less commonly referred to on a 64-bit architecture. But in theory, it would be 128 bits if you used it. Now, there are other things called quad words and larger units, but these computing typically doesn't standardize terms for larger data sizes as strictly as it does for the others. But the progression basically typically continues following the pattern of just doubling. So it's crucial to understand the terms for programming, especially in contexts where memory and data representation precision are important, such as system programming, embedded systems, and whenever you're dealing with assembly language or hardware level programming. Because different operations and different data sizes require different amounts of memory and has different instructions as well. So these units provide a clear language to specify exactly how much data is being discussed. Now, I want to talk to you about the stack pointer. And what we have here, I've written a simple example of a program that demonstrates how the stack and the stack pointer are used. Now, this program performs basic operations. It saves the register value to the stack, and then it retrieves it from the stack into a different register. So this demonstrates the push and pop operations, which you would commonly use in a stack in an assembly language program, but I'm not using the instruction push or pop here. I'm actually loading it directly and moving it around. Now, again, section.text declares that the following code is part of the code section. The global main says that this starts the main label as a global symbol, and we discussed that before. And then what it does here is it loads the immediate value in hex 1, 2, 3, 4 into register X5. Now, I've just used X again. here, but it's just to differentiate, stack pointer x5, x6. We can use we could use A1, S1, S2. It's largely irrelevant, but I'm just going to use the x values here in this example. Now, so all we do here is we load this into the x5 register, and then we decrement the stack pointer to make space for the 32-bit value. Now, stack pointer, the stack starts at a high point in memory and it gets pushed down. So if you can imagine those cafeteria stacks, which is what these are named after, where you push the tray down on it, as you push the tray down, the metal bit that holds the tray gets pushed further and further down. So the spring gets pushed further and further down with everything you put on the stack. So that's why it's called a stack. So it starts at the top and it's being pushed down each time you put something on it. So remember that. It's quite important. You can get confused and people think you're growing the stack. Well, you are growing the stack, but you're pushing the memory address down to make space. So anyway, we increment to save space for the 32-bit value. And then SW is store word. We haven't seen that one before, but we store the value in X5 to the stack pointer. So we're pushing it onto the top of the stack at its current location. Then we pop the stack into X6. So what we're doing here is we're loading, we stored from X5 and now we're loading into X6 the value at the top of the stack, and then we increment the stack pointer. Remember that, so this is 4 rather than -4, and that basically removes the value. So it is actually technically still there until it gets overwritten, but we've moved the pointer away from it so that the next value won't go there, and then we just exit. So if we run this program, but we use GDB because we're not got any output, so we're going to have to run this in GDB, and we'll put a break on main, and then we'll run it. So we want to see information, but you can't just do information registers or I space R. And the registers we want to look at are the stack pointer, X5, and X6. So let's look at their current values. So X5 is 2, X6 is more some random thing, and the stack pointer is at 1B0. Now, the first thing we're going to do is load that hexadecimal number into X5. So you can now see that it is now hex 1234, which is 4660. X6 has not changed and the stack pointer has not changed, but the next command will change the stack pointer. So we go ahead and run that, and then we'll look at the stack pointer. And you can see that the stack pointer has now gone down to AC. So it was B0, it's now AC. So it's decremented this stack pointer. X5 is still the same, and X6 is this random value that was just in there. We'll run the next command. Sorry, we're just loading the value into X6, or we will after this step. So we run that, and we now see that X6 has been loaded. So what's happened here is, if you remember, we pushed the value 1234 hex 1234 onto the stack, and then we've popped it off the stack into this register, and now both registers are the same. And we can just now it's just going to exit, exit normally. So so all we did there was we just pushed this on to loaded it into X5. We decremented the stack. We loaded the value in X5 into memory on the stack, and then we popped that back out into X6, and then we removed it by just pushing the stack back. So I mean, basically, we put a value on the stack and we received the stack, and then we ended the program. So this program illustrates the functional operations for working with the stack in RISC-V, pushing data into the stack and popping it back offward. You must remember that the stack grows downward from higher memory addresses to lower ones, which is why we always decrement the stack pointer when we push and pop it. So what we've got here is a really simple program to increment and decrement the stack, and then put values on the stack and pop them off when you need them. Typically you would use the stack to store values when you don't have enough available space in the register, or if you're going to store it and you're going to pull it back out frequently to do updates. Or you're calling functions that are going to clobber everything, so you store all the data before you call the function, and then you restore it afterward from the stack. But the stack is a very useful bit of memory that helps you to just move things in and out. Now, we've covered all the registers and most of the naming conventions on the registers and all of the stack. Next time we're going to go sort of deeper into this, and we will look at some more sort of in-depth look at data, really, and the data that you're going to use. But if you like this series, please like and subscribe, especially like. Just let me know that you like this sort of thing, so that I'll keep on doing it and persevering. Otherwise, you know, I can go do something else. But thank you very much for watching. I hope this was useful for you. I appreciate your time, and have a good day.